Hello, in this video we want to look at the graph of functions of two variables. So let's begin with the definition. If f is a function of two variables with domain D, then the graph of f is the set of points x, y, z in R3 such that z equals f of xy and xy is in D. So as an example, let's plot the function f of xy equals 6 minus 3x minus 2y. Now, I've plotted some things out already. We will then transition and do this in Mathematica. So first of all, notice that this is a plane. The reason why this is an equation of a plane is because the x and the y, they only have exponent 1. So there's no way that there's any curviness going on. This is some sort of straight line or straight plane. And the reason it's a plane, not a line, is that we've got two input variables, the x and the y. Okay, so this is a linear function, so to speak. The exponents are only 1. That's why I know it's a plane. So if I could figure out where the plane intercepts the x-axis, the y-axis, and the z-axis, then we could just connect the dots and we'd be pretty much done. So to do that, let's start with x equals 0, y equals 0. In other words, we won't move out in the x or over in the y. It'll just give us our z coordinate. So we evaluate f of 0, 0, plugging in, that equals 6. So the point 0, 0, 6 is a point on our plane. Similarly, if x is 0 and z equals 0, then we have the following. 0, that's because z equals 0, equals 6 minus 0 minus 2y. In other words, y equals 3. So that point is plotted over here. 0 in the x, 3 in the y, and 0 in the z. And lastly, if we let y equals 0, z equals 0, and we plug in, we find that x equals 2, and that point is plotted right here. And so connecting the dots, we get some lines, and then connecting the lines there with a set of points, that's our plane. So we have a tilty plane. It does not pass through the origin, but it's kind of slanted outward there, and we have found the x, the y, and the z intercepts. Okay, let's go over to Mathematica. We'll plot that plane and then we'll also do some additional examples. Okay, so when you go to Mathematica, let's click Notebook. And I have a blank page here at the top of the screen. I'm going to click Palettes, Classroom Assistant. And what that brings up is our Classroom Assistant. It just makes some of the tools a lot more accessible and right at our fingertips. So let's create a new input cell. I'm going to do a 3D plot. So let's go down here to 3D, plot 3D. The function we want to plot is 6 minus 3 times x minus 2 times y. And let's plot the x variable as x goes from 0 to 10. And let's plot the y variable as y goes from 0 to 10. Shift enter, and we get that tilty plane. So that looks pretty good, except we don't really know what is the x and the y and the z axis. So let's put a comma here and we'll put some extra options. So if we go over to options and click on axes, so let's click on axes label and we'll choose x, y, and z. And so now we really nicely see those axes. Okay, great. Let's do another example. Let's click on Input, Plot. We're going to plot 4x squared plus y squared. And let's plot x as x goes from -5 to 5. And let's plot y from -5 to 5. Shift enter. And that plot looks really nice. Now the question is, what happens as we take on more x and y values? So let's just bring this out a little bit, maybe 15. And we still kind of have that same general shape. Okay, let's do another plot. In this case, let's do a 3D plot. And the function we're going to plot is parentheses x squared plus 3y squared times e. Now notice that there's a e, which is a irrational number. It's on the classroom assistant palette. It's right next to pi. If you were to type an E from your keyboard, notice that that's different. So there's a difference in between those two symbols. We do want the E from the classroom assistant palette, the irrational number E. And we're going to go E raised up to the negative x squared minus y squared, and we'll plot from x goes from correct choice, but you do want to make sure you see the high points and the low points of the function, and that looks really good. You can see the low point down there, the minimum, and you can see there are two local maximums. Okay, so next let's plot sine of x plus sine of y. Notice that the trig function has a capital letter for s, and also that the argument is in square brackets. Let's plot x from negative pi up to pi, and I'm going to copy paste those values again for my y's. Shift enter, and that's beautiful. Maybe there's some more interesting features if we were to go out negative 2 pi to 2 pi. Sure enough, looks kind of like an egg carton. Beautiful visualization. Lastly, let's plot the function. Looks like a fraction. In our numerator, we have sine of x plus sine of y, and in the denominator x times y. Notice that if you just do xy, Mathematica will think that's a new variable xy, and we mean x times y, so you do need to either put a space in between or the multiplication symbol. Again, let's plot from negative pi up to pi, and let's see what happens. Now this plot looks very bizarre, and the reason it looks so strange is because when x is 0 or when y is 0, our function is undefined, and so we can see that there's some very unusual behavior. Mathematica is trying its best to plot, but it's having a hard time because of those places where the function is undefined. So we could make the plot look a little bit better by adding in some exclusions. If we go down here in the options area and we go under other, and then you click exclusions. So the set of exclusions will be x equals 0. Notice there's a double equal sign, and y equals 0. So those are the points we're going to exclude from our plot. And that looks a little bit better. We can start to see what's happening as we approach the x and y axis from one side or the other. Our function's kind of dipping down towards negative infinity or scooting up towards positive infinity. Now our z-axis only goes from negative 2 to 2, so we're not seeing those vertical asymptotes totally, but at least we have a better picture of what this graph looks like.